You've seen it a million times in the movies, right? The jump to light speed, the warp drive kicking in. It's awesome. But what if I told you that for more than 100 years, the laws of physics as we understand them have put up this giant universal stop sign? So let's dig into why traveling faster than light might be way more than just an engineering challenge.
And this is the question that always comes up, isn't it? I mean, think about it. A smartphone would have been straight up sorcery 1,000 years ago. So is faster than light travel just the next impossible thing we'll eventually figure out? Or are we dealing with a completely different kind of problem here?
To figure that out, we really need to understand what this so-called barrier actually is. Because it's not just a guideline or a suggestion. Physicists consider the speed of light to be a fundamental speed limit for the entire universe. So let's look at the evidence. Now, this is exactly the right question to ask. You know, science isn't about just taking things on faith, not even from a genius like Einstein. So if there really is a cosmic speed limit, where's the proof? What actually happens when we try to put the pedal to the metal? And here's the thing. We have been trying. This isn't some dusty old theory sitting in a book. For decades, in some of the most complex, most powerful machines humanity has ever built, we've been pushing this universal speed limit just to see if it'll crack. Okay, so what if all these experiments actually shown us? When we push these tiny little particles in these incredible machines, what happens? Let's take a look at the data. So inside these giant rings, like the Large Hadron Collider at CERN, we take tiny particles, protons for instance, and we blast them with just immense amounts of energy. We get them moving at unbelievable speeds, like over 99.99% of the speed of light. But here's the wild part. No matter how much more power we pump in, they never cross that finish line. They just get infinitesimally closer. And what we see every single time is the real heart of the problem. As you pour more and more energy into an object to speed it up, the return you get, the actual increase in speed, gets smaller and smaller. To get that last tiny fraction of a percent closer to light speed, the energy you need becomes, well, it becomes astronomical. It's a curve that just shoots up towards infinity. Just let that sink in for a second. Infinite energy. That isn't just a fancy way of saying a whole lot. The math and the physics are telling us that to get any object that has mass to the exact speed of light, you would need an amount of energy that is literally, mathematically, infinite. And to give you some kind of scale for what infinite means, well, this number here, that's the estimated total energy of everything in our observable universe. Every star, every galaxy, every single black hole. If you could somehow gather all of that energy, the whole shebang, and focus it on one little spaceship, it still wouldn't be enough. Our universe has a finite amount of energy. The requirement is infinite. And this is the moment we have to switch gears, because this isn't an engineering problem anymore. It's a physics problem. The speed of light isn't some barrier we can just smash through with a better engine. It seems to be a fundamental rule that's woven into the very fabric of space-time itself. And it all boils down to this one incredibly strange but proven fact about our universe. No matter how fast you're moving, whether you're standing still or zipping by in a rocket ship, if you measure the speed of a beam of light, you will always get the exact same number. It's an absolute constant. It never changes. Okay, and that one simple-sounding observation is the entire foundation of Einstein's theory of special relativity. Here's the aha moment. If the speed of light is absolute for everyone, then something else has to be relative. And that something else is time and space. As you get closer to light speed, time for you actually slows down, and space contracts relative to someone watching you. It's this warping of space-time that prevents you from ever reaching that finish line. It's an unavoidable consequence. And look, this isn't just some abstract theory we talk about in a classroom. We rely on it every single day. The GPS in your phone only works because we account for relativity. The satellites orbiting Earth are moving so fast that their clocks literally run a tiny bit slower than ours down here. If we didn't correct for that time difference, a difference predicted perfectly by Einstein, your GPS would be off by miles within a single day. You know, the true power of these theories is in their predictions. Einstein's work didn't just explain the speed limit, it also predicted that massive objects could literally warp space-time, bending the path of light itself. And when astronomers pointed our best telescopes at distant galaxies, what did they see? They saw that exact effect, light being bent and distorted into these beautiful rings and arcs. It was stunning proof that his revolutionary ideas were right. So, If the speed limit is absolute, does that mean we're just stuck in our little corner of the galaxy forever? Well, maybe not, because the very same theories that lay down the law also seem to hint at some, well, let's call them tantalizing, highly speculative loopholes. This is where things get really interesting, and the line between hard physics and science fiction starts to get a little blurry. If you can't travel through space faster than light, what if you could find a way to travel through less space? And that, of course, brings us to the famous idea of a wormhole. Now, the key here is that you're not actually breaking the speed limit. Inside the wormhole, your ship would still be chugging along at sublight speed. But the wormhole itself would act like a tunnel, a shortcut through the very fabric of spacetime, connecting two points that could be light years apart. Its formal name is an Einstein-Rosen bridge, and it's a fascinating, purely mathematical idea that just kind of falls out of the equations of general relativity. The classic analogy is perfect. Imagine spacetime as a giant sheet of paper. Instead of traveling all the way across it, you could just fold the paper over and punch a hole straight through. Now, before we all get too excited and pack our bags, there is a huge catch. A few of them, actually. First, we have absolutely zero observational evidence that wormholes are real. They're just a possibility in the math. Second, our theory suggests that to keep a wormhole from collapsing on itself instantly, you'd have to prop it open with something called exotic matter, stuff that has negative mass. And we've never seen anything like that in the entire universe. So, after all of that, what's the verdict? Is our dream of exploring the stars, of traveling faster than light, is it truly impossible? This slide right here really gets to the heart of it. Think about it. We didn't invent airplanes by defying gravity. We invented them by mastering the laws of aerodynamics to work with gravity. That's the difference. Trying to go faster than light doesn't seem to be about mastering the rules. It seems to be about trying to break a fundamental rule that the universe just doesn't let you break. And that's really the key takeaway here. Breaking the sound barrier was an engineering problem. We just had to build a better, stronger plane. But breaking the light barrier appears to be a fundamental physics problem. It's not a technological wall we haven't figured out how to climb yet. It looks more like it's a structural feature of reality itself. But you know what? That's the beauty of science. We can only ever draw conclusions based on what we know right now. And it's right there, on the boundary of our knowledge, in that blurry space between what seems physically impossible and what's just technologically undiscovered. Well, that's where the most exciting questions are. And that's really what this is all about.